a little bit of historical background. And in this problem here, in exercise 1, you have a list of countries, and these countries have a region associated with them. For example, in North America, there are 23 countries. Now remember, North America covers everything from the Arctic pole down to the Antarctic pole, right? Okay, the North Pole to the South Pole, starting in Canada and going all the way down to probably Argentina, which is the southernmost country in North. Oh wait, I'm sorry. We're dividing the Americas up. 23 in North America. It's not clear whether Central America is considered part of North America or South America. I think some countries in Central America are considered as part of South America. Mexico, in fact, may be part of North America. I'll have to double check that, okay? 23 countries in North America. Gee, it looks like, that's curious. I didn't know there were that many countries in North America. Okay, 12 countries in South America, 47 countries in Europe, 44 countries in Asia, 54 countries in Africa, 14 in Oceania. I don't know if I'm pronouncing that right. Oceania. Okay. So the idea is, if you consider each of those outcomes, that is picking a country from one of these regions, and you would assume that you're picking these at random, okay? So we're going to talk about a function called probability, and the domain of probability, it's a bona fide function, and the domain are the subsets of the population, okay? So if we consider a probability of selecting from one of these countries, then what we can do is the following. We can take a relative frequency. When we talked about the coin tossing experiments, we were able to actually calculate the frequency table for that experiment. This is another experiment where we select one of these countries and ask for its relative frequency or its probability. So now we have this new term, which is really in many instances just a relative frequency. What is the ratio of the number of countries defined by, let's say, A, where A is the event here, let's call it the event, that the country is in Asia. So you're saying, okay, well, I know that there are 44 countries in Asia, so the relative frequency of picking a country from Asia, assuming that they're all equally likely to be picked, is just the ratio of the number of countries in Asia over the total number of countries worldwide here, split up into these regions. So there we're using again our notion of relative frequency, okay? So the probability is the relative frequency, 44 over 194. And there we have a fraction. We can go to the calculator if we want and round that fraction to 2 decimal places, and that would be 0.23, okay? Now, can you leave it as a fraction? Sure. The fraction is just as valid as the decimal value here, okay? So you can leave it as a fraction, Or if you want to, you can divide 44 by 194 and come out with, my calculator here is expressing this fraction out to 9 places. So if I round it to 2 places, it's 0.23. Now again, you know where the 44 came from, right? There are 44 countries in Asia. So you know the numerator is that number 44. That's the frequency, that is the number of countries in Asia. And the denominator is the sum or the entirety of the number of countries. So if you were to add up 23, 12, 47, and so on across all these different regions, you would get our denominator here, which is the sum total. Okay, 44 over 194, round that to 2 places and you get 0.223. Or as I said, you can leave it as a fraction if you want. And it would be nice if you simplified it, that is, find what the common factors are and cancel those out in top and bottom. If you did that, you'd get 22 over 97. So any one of these 3 expressions that you see up here is a valid answer. You can leave it as a fraction, or you can reduce it as a fraction, or you can simply leave it, you can round it as a decimal, display it as a decimal, okay? Now, we won't go down this list and do all of these here because we do it in the very same way that we did Asia, right? The probability of Europe is the number of countries in Europe. We're told that there are 47 countries divided out by the total number of countries in all of these regions. So we get 47 over 194, which is approximately 0.24, okay? Any questions about number 1 here? There you see all the probabilities. Now, again, what is what is the sum of all of these different probabilities here? Now, remember, you've done several exercises with relative frequency, and you know that the relative frequencies always add up to 1, okay? And that's true of this example here. If you were to add these 5 fractions or 5 decimals, you'd get the value 1, okay? The other feature about these numbers, these p numbers or probability values, is that they're always between 0 and 1, aren't they? Okay, probability is a number between 0 and 1. Okay, so that's basically a definition of a probability function, is that all the values are in the interval 0 and 1. Now that's the closed interval. So sometimes probability is 0, sometimes probability is 1. Okay. All right. Typically, probability of 1, we would call that the certain event. The probability of the sun rising tomorrow, you know, that's a certain event, and that has probability 1. And the probability it will rain in San Diego today, there's no rain in the forecast, so we could approximate that probability with a 0. We'd like to have some rain, but unfortunately, we won't get any rain today. Okay, all right, now, okay, let me Let me reduce this a little bit. Okay, you know my my adventures with the mouse here. Okay, all right. So any questions about number one, finding a probability, and think of this probability in some sense as a function which takes subsets of the population and converts them into a number between 0 and 1. Okay? All right. No questions about number one?
My question is just that I added up all the like percentage values, and when you add them all up, it actually only gets to 88%. So like the 0.23, 0.24, 0.07.
54, 60.88. Okay. Good catch. Okay. Yes, I just did the sum, and you're right. 0.23 plus 0.07 is 0.3. If you add that to 0.24, you get 0.54. And 0.54 with 0.06 gives us 0.6. And 0.6 plus 0.28 is 0.88. Okay, so there's a region in the world that's not accounted for with all of these countries here. There are 16 other, it looks like, yeah, okay. And if we knew that number, then we could take the probability of what's known as the complement, right? The complement is the event that is contrary or contains no elements of the other events. All right. So what's the complement of the event that it rains today in San Diego? What would be the complement of that event? Yeah, go ahead, anybody?
0?
Well, we're talking about an event now, not probability. So the event would be it does not rain in San Diego.
So
It
just
would
like
be
sunshine.
the total sunshine versus total rain, or some rain versus no rain. Those would be complementary events. So one student noticed that these probabilities don't add up to 1, so there must be some region in the world that we're not taking into account. Okay.
I think we're not counting the North America ones.
N.
Yeah, the North
Okay.
America isn't in there.
Okay. All right. So let's see, what is the probability of North America? Let's calculate that really quickly. That would be 23 divided by 194. And that gives us about 0.12. So that would take us, so that would give us, so our complement is the countries in North America, and for some reason that's not listed here. So that's a good catch. I think we all learned something there, right? Okay. All right.
Awesome,
so you learned a couple of things. The complement is North America. That has probability 0.12, and that's not in this list. Okay. All right. Other questions about 1? Okay. So let's go to number 2. And here, number 2 is a standard deck of cards. Okay, now we've all played cards. We've played gin rummy. We can play poker. We can play pinochle, if anybody knows what that is. You know, there are lots of different card games. Typically, a standard deck has 4 suits. Each suit has 13 cards in the deck, And the suits are hearts, diamonds, clubs, and spades. Okay, so the deck of 52 cards is sitting there in front of us, and we're going to draw a card. And remember, you know, typically when card games are played, people shuffle the deck. And what are they doing there? Well, they're trying to take any bias out of the deck. Although a simple shuffle of a deck, typically when the dealer takes a new deck of cards, typically he'll take a brand new deck, remove the cover, remove the wrapping, and then what does he do? He shuffles the deck, okay? Because typically when the cards are newly packaged, they may be they may be in their numerical order, okay? In other words, let's say the card is, the deck has the hearts on top of the deck, ace through king, and then followed by the diamonds and so on. So by shuffling them, we're sort of emphasizing the fact that we want to get a random selection, okay? However, some of you might think, well, if the cards are in order, and I keep shuffling this deck, they may actually fall back into order somehow. All right, so anyway, the notion of shuffling is a reassurance that the selection is completely random. That is, each card is equally likely. All right. You know, if we didn't shuffle the cards, it's likely that the red cards, the hearts and the diamonds, would be on the top of the deck. Now, you know, you've seen the magic shows on TV where someone is asked to draw a card, and they can actually pick out any card that they want in the deck, right? They can pick from the top, they can pick from the bottom, they can pick from the middle. So our experiment here is, let's draw a card, and we want to find a probability that the card that we draw is red, okay? And since we know how the deck is constituted, that is, it has 13 hearts and 13 diamonds, all told, there are 26 red cards in a standard deck. And if they're all equally likely to be drawn, then the relative frequency should be the number of red cards in the deck, which is 26, and compared with the total number of cards in the deck, which is 52. So it's just a half. So you have a probability or a chance of about 1/2 of drawing a red card, okay? Again, you're using your intuition about relative frequency. How many cards in the deck satisfy the event it is red, okay, divided out by the total number of cards, and that would be 26 over 52. Okay. Now, let's go to the next one. What's the probability of drawing the club? Well, we know that there are 13 clubs in the deck, right? That's the way the deck is constituted. So its probability would be 1/4. You have probability 13 over 52 of drawing a club. Okay. And in the next one, what is the probability of rolling an even number of dots with a fair 6-sided die numbered 1 through 6? Okay. Well, let's write out the event of an even number. So let's call that C. And we know that it consists of 3 elements, 2 dots on the face, 4 dots or 6 dots. Any other roll would come up odd. So the complement of the even numbers is the set of odd numbers. And there are 3 even numbers out of the 6 faces that could appear in your experiment. So again, we get 1/2, 3 out of 6, okay? And what's the complement of C? Well, C is draw an odd number, and there you would see the probability of the complement of C would be 1/2 as well, okay? Another way to think of the probability of the complement is simply to subtract from 1. If I want the probability of an odd, I simply subtract the probability of the even, because even is its complement, and subtract it from 1, and that'll give me the probability of the odd numbers. In this problem, it's pretty obvious, but I just want to give you the heads up because we will use the notion of a complement from time to time. Okay? And same with the probability of rolling a prime number. So the primes are, okay, here the primes between 1 and 6. What are the 3 prime numbers between 1 and 6? Who can tell me what those are?
1, 2, and 3.
No, 1 is not considered a prime number. Typically, the prime numbers start with 2. So you have 2 and 3. What is your other prime?
5.
5. Those are the 3 prime numbers, 2, 3, and 5. Okay? So once we've identified those, then we take the relative frequency, the number in our event, which is 3, divided by the total number in the, what we would call the sample space, okay? The sample space is simply another name that's used in probability for the population. So 3 over 6, and that gives us the 0.5. Question?
Professor,
Yeah,
Question.
but
there's some,
someone just texted, or like somebody just sent a message and their Wi-Fi went out and they're in the waiting room, so they're just waiting on you to let them back into the Zoom meeting.
Okay, okay. Let me go ahead and do that.
Sorry to interrupt you.
No, thank you for interrupting me because we don't want anybody to sit in the waiting room.
Yeah, I just feel
Okay.
bad. I don't want him missing class.
Good. I'm glad you've okay. All right. Everybody in now? Who's not in? Okay. All right. So let's go ahead and move on. Okay. So now you're all warmed up. You're thinking about probability. Okay. And so let me go back to our view here. Okay. So there we go with our. Now this problem here gets a little more complicated, right? Okay, so let's read what we've got here. It's a special deck. It has 10 cards. And so this special deck has 4 green cards, 3 blue cards, and 3 red cards. Okay? 4 plus 3 plus 3 is 10. So this 10-card deck has these 3 different types, these 3 different colors of cards. When a card is picked, again, we're assuming random selection. Each of the 10 cards has an equal likelihood of being drawn, okay? We look at its color after it's picked. And here's a joint experiment where we pick a card out of this special deck, and then we toss a fair coin. If we say toss a coin, we assume that the tosses are equally likely. That is, the probability of a heads is a half, and the probability of a tails is a half. So you see what we're doing. We're picking the card first, and then we're tossing a coin. okay? So what is the sample space? Okay, so that's a subset of all of the possibilities of picking a card first and tossing a coin secondly, okay? So let's go ahead and symbolize or write out what this set is, the set of all of the outcomes of first picking a card from this deck of 10 cards and then tossing the coin where the probability of a heads is equal to a half, okay? Well, let's do this. Let me denote the sample space in the following way. Since there are two joint events going on here, I'll denote the first element in this ordered pair in our sample space as G if the card is green, okay? We've got green, blue, and red in our special deck. So let's denote the sample space as a set of ordered pairs. The first element in our ordered pair is going to be the card that we drew, and the second element in the ordered pair will be the outcome of the coin toss. So if we pick a green card first, then we can get either a heads or a tails on the coin toss. Similarly, with the blue card first, we get the heads and the tails on the toss. Red card, same thing. So again, remember our counting principle from algebra says that the number of ordered pairs would be 4 times 2, right? 4 color, let's see, 3 colors, sorry, not 4, but 3 colors, green, blue, and red, followed by 2 outcomes in the coin toss. So there are a total of 6 elements in our sample space here if we count out using the counting principle. 3 times 2 gives us the 6 ordered pairs, all right? Now, another thing to notice here, after you've picked your card, does it in any way affect the probability of heads or tails? Suppose you drew a blue card first. Now you toss the coin. Does the probability of the coin toss have any effect or show any effect from the fact that you saw a blue card being selected in the first part of the experiment? Any ideas on that one? We're saying that the probability of a heads is a half, okay? Any ideas? Does the card affect the probability of the heads?
No.
No, it doesn't.
No.
It doesn't, because in probability, we say that the events are independent. I used this term when we were doing the coin tossing experiment in worksheet 2. I said that if you toss the coin 3 times, the probability of a heads on the second toss is still a half. It doesn't matter what you saw in the first toss. Those 2 events of tossing a coin twice are independent. Later, we'll talk about conditional probability, where we ask for the probability of an event given some other event has already occurred, all right? But in this experiment, you clearly see that the coin toss doesn't depend in any way upon the card that's drawn, okay? So whether you pick a blue or a red or a green in your card selection has no bearing on the probability of visualizing a head on the second part of the experiment. So the way we're going to do this experiment is take the event A, which is the event that a blue card is picked first, followed by seeing a head on the toss, okay? So we're going to take the probability of blue, all right? And since there are 3 cards in this special deck of 10 cards, that probability or that relative frequency is 3/10. And then we'll multiply it by 1/2, okay? And that gives us 3/20 or 0.15. Again, as I said, you can leave it as a fraction. You don't have to convert it to decimals. Is everybody okay with part A here? Part B, part A and B. Notice that we simply get, using what's called the multiplication rule of probability, if 2 events are independent, then the probability of their joint occurrence is the product of the probability of the single occurrence, card followed by the toss. Okay. All right. Now, mutually exclusive means that they are separate in terms of their outcomes, right? Now, B is the event that a red or a green is picked, all right? So what is the answer to these questions? Is the event that a blue card is picked first, all right? Does that have any bearing on a redder card being picked? Okay, all right. Well, notice that they're mutually exclusive because they don't happen at the same time. You can't pick a card that is blue and at the same time is red or green, okay? So the probability that you get a blue card and either a red or a green card is 0. Okay, so on the draw of the card, you either get a blue card or not. So the blue card and not blue are mutually exclusive. Okay. What about C here? C is the event that a red or a blue card is picked. Now, let's suppose that you do pick a blue card, all right, first. And now let's ask, what's the probability of picking a blue card or a red card, a blue card or a red card, all right? Now there, you can see that they're not mutually exclusive because they both involve the blue card, right? So you can have a blue card pick, and then in fact, C says red or blue is picked. Aha, I've picked a blue card, and so A and C are not mutually exclusive. C says pick a blue card. A says a blue or a red. A says pick a blue card. So you can see that those two events overlap, right? And blue is the intersection of their overlap, okay? All right. And they're not mutually exclusive. And if we pick blue, which is A, then we've already satisfied C. So the probability of A and C is simply the event that a blue card is picked. And that's 3/20 here, okay? Yeah, probability of A. And we saw that the probability of A was 3/20 in part A here. Any questions about number 3? Okay, on your midterm, I will give you problems like this. Not very many, but there could be a problem in probability. Now, later, I want to talk about MyLab statistics and keeping up with your homework there. And we'll come back to that because in your MyLab statistics, you will have problems in probability. So before your midterm, you need to make sure that you've touched all the bases with MyLab statistics so that you're well prepared for the midterm exam. Now, you're probably wondering, well, when does the midterm exam happen? If you look in your syllabus, I did stick it in the middle of that list. Maybe later we can look at that list. So it's going to appear in week 7 or 8. We're in week 4 now. So in about 3 or 4 weeks, we'll have the midterm. Sounds like a lot of time, but you know, time flies when we're having fun, right? Okay, so let's see. Week 7 is the last week of September, and week 8 would be the first week of October. And I'll announce, it's more likely going to be, I'll give that to you in the 8th week, all right? And so, you know, so you need to put that first and foremost. The midterm, let's say, is week 8, first week of October. All right, and I'm now in September. Today is September the 8th. So, you know, most of September is still out there. And so you need to resolve to do your homework in MyLab statistics so that you can prepare. These worksheets are good preparation for the exam, but you need to do more. Okay, you need to do more. So be sure that you are opening up MyLab statistics and going through the problems there in the probability chapter. Okay, now we come to the final exercise here. No, I'm sorry, 4th exercise. Okay, now in this exercise, we're given a scenario. We are told that these events, C and D, have certain relationships. The first relationship is that the probability of the event C is 40%, 4/10, or 0.4. This other unnamed event, D, has a probability of 1/2. Now, what is this notion here? Okay, this is what I mentioned before, conditional probability given, and the way we read out this symbol here, it's written P of C / D, and that slash is basically the condition. So the way we read this out typically is probability of C given D. So this notation in words is simply the probability of C given D. So let's go back to rain and sun, okay? What's the probability of sun tomorrow, given that we had sun today? What's the probability of rain tomorrow, given the probability of rain today? All right. So the weather forecaster, you know, is giving us the forecast for rain tomorrow, and it's based on information that he has about the storm that has just come in, and is that storm going to end today and there will be no rain tomorrow, or is the storm at the beginning or the middle of the storm, and yes, there's a high probability that there will be rain tomorrow, given it rained today. So that's the notion of conditioning, okay? So this third scenario is the probability of C given D. Now, notice the conditional probability of C given D is different than the probability of C, isn't it? The probability of C is just 0.4, but the probability of C given D goes up. because we have new information, D, and that's associated with C, isn't it? Okay, so the probability of C given D is 0.6. Now, we want to find the probability of their intersection, that is the probability of C and D, okay? So let's do that. We'll use what's known as the multiplicative property, where we take the probability of C and D, and invoking that property, the probability of C and D is the probability of D times the probability of C given D, okay? That's called the multiplication probability of probability theory, okay? Now, if these two events, C and D, are independent, okay, then the probability of C given D, that is the probability of C conditioned on D, will just be the probability of C. That's another way to describe independence. But these two events are not independent, are they? Okay, because we're told that the probability of C given D is 0.6. Given the fact that we've seen D, that changes the probability of C to 0.6. If we don't condition on D, the probability of C is 0.4. Okay, so using this multiplication property, now we see that the probability of C and D is the probability of D times the probability of C given D. We have both of those factors, don't we? We're given the probability of C of D, okay, delta, the probability of delta up here is 0.5, and the probability of C given D is given to us to be 0.06. So using our multiplication property, we get this product here, 0.5 times 0.6, and that gives us 0.3. Okay? All right. Now we can answer part B. Remember that if two events are mutually exclusive, then the probability of their intersection is 0, right? They're mutually exclusive. One event is contained in the complement of the other event. So since we know from part A in this problem that the probability of their intersection is not 0, it's 0.3. So they can't be mutually exclusive, all right? Their intersection has positive probability here. In fact, it has probability 0.3, right? Furthermore, they're not independent in part C here because we're told that the probability of C given D in the scenario is 0.6. That's different from the probability of C, okay? So they're not independent. Okay? And now finally in part D, we come to what's known as the addition rule of probability. And this is the probability of C or D. Either C happens or D happens. What's the probability of their joint occurrence? That is, their either C occurs or D occurs. And the so-called addition rule for probability tells us that it's the sum of the probabilities C and D minus the probability of their intersection, okay? And we have, in the scenario, the probability of C is 0.4, the probability of D is 0.5, then we subtract the probability of their intersection, and that's 0.3, and when we add 0.4 and 0.5, subtract 0.3, we get 0.6, okay? All right, so we know that there's some overlap between C and D, and if we simply add the probability of C with the probability of D, we're sort of accounting for that intersection twice, okay, because there's some C and D, so we have to subtract out the probability of C and D once, and that gives us the correct value here of 0.6. Okay. All right. Now let's use the multiplication rule again to find this probability in part E. Part E is find the probability of D given C. Okay, now the probability of D given C, here we can use either the multiplication rule and note that the probability of C and D is the probability of C, right, given or times the probability of D given C. Okay, so let me write this. The probability of C, oops, we didn't want that, did we? Okay, all right. This is equal to, okay, this is equal to, let's see, I guess what I want to do here is multiply. So let's multiply, let's see, yeah, so probability of C times, actually, let me do it this way, and then you'll see it. Probability of C and D. Okay, and remember, here we wrote that joint probability as the probability of D times the probability of C given D. Okay? Now, it's equally true that now we can condition on C, right? Just over here, up here, just reverse the roles of D and C here, and you get an equality here. That is, this is the probability of D here, probability of C, okay? Now, that means that we're going to condition on C. So we'll take the probability of now, instead of C given D, we take D given C. And, okay. So here we have two expressions for the probability of C and D. We either condition on D and multiply by the probability of D, or we condition on C and multiply by the probability of D given C. Either way is correct. Okay, now, if we solve this equation for probability of D given C, we get this equation up here. Okay, the probability of D given C is the ratio of the probability of C and D divided out by the probability of C. Does everyone follow that now? Here we have the multiplication rule where we have conditioned on D. So the probability of C and D is the probability of D times the probability of C given D. Down here, okay, we have the same thing. Instead of conditioning on D, we'll condition on C. And now the multiplication rule is probability of C times the probability of D given C. Okay, and now we can solve this equation here, okay, for the probability of C, or the probability of D given C, So we're solving for this piece. All we have to do is divide by the probability of C. And we know that the probability of C is not 0. So we can do our division here. So the probability of D given C is the probability of C and D divided out by the probability of C. The probability of C and D from part A is 0.3, and the probability of C is given to us to be 0.4. So we get 0.3 over 0.4, and that's 0.75, or 3/4. Any questions about number 4? The two key tools for number 4 were the multiplication rule. Okay, you can write it this way, or you can write it this way, right? You can either condition on C, or you condition on D. Either way, you can invoke the multiplication rule and obtain either this one, or this one. They're both equal. In this one, I conditioned on D. In this one, I conditioned on the other one, which was C. But writing it this way allows me to solve for the probability of D given C. Do you all see that? Okay. And now converting this equation here to this equation here gives me a way to calculate the probability of D given C, and that gives us the 0.75. Okay. Okay, now let's go to the last problem here. Let's see what we've got up here. We have a deck of cards. The number of cards in the deck is 10, and 6 of these cards are green, the other 4 are yellow. Okay. Now, we're going to draw 2 cards at random, one at a time, one after the other. But in this experiment, we're not going to replace the first card back into the deck. We're going to keep it out, right? That's what you would normally do when you would draw cards from a deck. Any card that you draw from the deck, you would leave it out. And now you have a deck of 51 cards. I'm talking about a standard deck of 52 cards. And, you know, in the magic show, the magician asks a person from the audience, pick 2 cards. All right, so they pick one, they keep it in their hands, they don't show it to the magician, right? And now they pick another card, but now the deck has been reduced. So that'll alter the probabilities of choosing another card, right? So let's see how this works out. Let's call G1 the event that the first card drawn is green. And we'll call G2 the event that a second card on the second draw is green, okay? So we're looking at G1 and G2, pick a green card on the first draw, leave that card out of this deck. That reduces the number of cards in the deck to 9 cards, all right, 5 of which are now green, and the other 4 are yellow, okay? So let's draw a tree diagram of this experiment. Okay, so we either pick a green card on the first draw, and the probability of picking a green card on the first draw is 6/10. Now, on the second draw, you either get green or yellow. Now, what's the probability of a green card on the second draw? Okay, so we're looking at this path, G1, G2. Well, if we've already picked a green card on the first draw, that leaves 5 green in this deck, and there are a total of 9 cards left over. So the probability of another green following the first green would be simply 5/9. So the probability of picking a green card on the second draw, given that you drew a green card on the first draw, is 5/9, okay? And I've listed all the probabilities for these 4 possibilities. Pick a card and follow that up with another pick, but you leave out the card that you picked on the first draw. Okay, does everyone believe this tree diagram here? Let's do one more. Let's pick a yellow card on the first draw, okay? And ask for the probability of a yellow card on the second draw. Well, the probability of a yellow on the first draw is just 4/10. There are 4 out of the full deck of 10 cards. So the relative frequency is 4/10. Now, what's the probability, given that you drew yellow on the first draw, that you get a yellow on the second draw? Well, you depleted your deck by 1 card, so now there are 9 cards left over. And you've already picked a yellow card on the first draw, so that means that there are only 3 cards left in the deck of 9, and that has probability 3/9 of a yellow on the second draw. Is everyone okay with the tree diagram here? Everybody okay with that?
Would you mind showing us how you made it, please?
How I filled in the
Yeah.
tree?
Yes.
The tree diagram is a branching diagram, depending on various stages in your experiment. We only have 2 draws here, but the key feature is that the deck is fixed at the beginning of our 2 draws. And the other feature of this experiment is that we don't replace. Okay, so let's do this path here. A yellow card on the first draw, followed by a green card on the second draw. Okay, so tell me, what is the probability of drawing a yellow card on the first draw? Go ahead.
I'm sorry, it cut out.
Oh, what's the probability of drawing a yellow on the first draw?
4, right?
Well, remember, probability is a relative frequency. So you have a fraction basically, right?
Right.
So what's the probability? You have 4 cards in the deck, that's correct. Out of a total of 10 in the deck, they're all equally likely. So what's the probability of drawing a yellow on the first draw?
10.
4 out of
4 out of 10.
4 out of 10. Okay, so it's 0.4. Now,
Oh,
you have to keep that first card out. And now your deck only has 9 cards in it, and 6 of which are green, but only 3 of which are yellow. Because you've already drawn the yellow card on the first draw and you left it out. So the probability of getting a green card, given that you have a yellow card on the first draw, the probability of the green on the second draw would be the number of green divided out by the number of cards in the deck. But you've reduced the deck by 1 card and you've left that out. So now he's selecting from the rest of the deck, which has 6 green and 3 yellow for a total of 9. So it's 6/9. Do you see that?
yes, I do.
Okay. All right. And so all I've done for a tree diagram is I've taken the initial situation, and if you choose green on the first draw, then you're going off in this direction. you either choose green on the second or yellow on the second. If you choose a yellow card on the first draw, then on the second draw, you either get green or yellow. But take a look at all of these probabilities out here, right? Notice that there is a 9 in the denominator there, because now you've reduced your deck from 10 cards to 9 cards because you didn't replace that first draw back into the deck. So your denominator changes. Okay, let's do the rest of these now. Probability of a green card on the first draw and a green card on the second draw. Okay, so that's this branch, this top branch of your tree diagram up here, where you get 2 green cards in 2 draws without replacement. So the probability that you drew a green card on the first draw is probability of G1. That's 6/10, right? That's your probability of drawing on your first draw a green card. Now you want to follow it up with another green card, but now you only have 9 cards in the deck, and 5 of which are green because you pulled out a green on the first draw. So the probability of getting G1 and G2, that is 2 green cards on 2 successive draws using the multiplication rule for probability, is 5/9. That's the probability of the conditional probability of drawing green on the first draw and following that up with another green on the second draw, times the probability of the green on the first draw. That's 6/10. So you get 5/9 times 6/10, right? And you can do your simplification there and get 1/3. The product of 5/9 times 6/10 is 1/3. Okay, and there you see it up here. Take your 6/10, multiply by your 5/9, and you'll get the probability of 2 green cards in the 2 draws without replacement. Okay. All right, in part C, find the probability of at least 1 green. Okay. Remember, you're drawing 2 cards. So what's the probability that you get a green on both draws of this situation? At least 1 green. I'm in C, not B. So the probability of at least 1 green, okay, means that you have at least 1 green in either one of your 2 draws, or in both draws, right? Okay, that would give you at least 1 green. The complement of that event is that they're both yellow. You got a yellow on the first draw and a yellow on the second draw. All right, any other outcome of the 2 draws would result in either 1 green or 2 greens. Okay, all right. So that's the probability here, that you get either 1 green, at least 1 green means that you have a green on the first and a green on the second, a yellow on the first, a green on the second, or both green. Okay? And notice that that turns out at least 1 green. Its complement is that they're both yellow. Now, why did I do it this way? I could have calculated the probability of at least 1 green using my multiplication rule on the tree diagram. And there I would have, the sum of those 3 different events, probabilities of those 3 events. Or we can take the complement, calculate the probability of the complement, which is easier really, and then just subtract it from 1, right? So we can denote the complement of an event, E, as E prime, okay? E prime in this experiment is that they're both yellow. Otherwise, you would get at least one green, wouldn't you? Okay, so let's calculate the event, calculate the probability that they're both yellow. Okay, so that's this branch of the tree, 4/10 times 3/9. And then we'll subtract that product from 1 to get the probability, all right, that you get at least one green. 4/10 times 3/9 is 1290, 12 over 90. Subtract that from 1, and you get 13 over 15. Okay. All right. Now, some of you did this in the following way. You said, well, at least one green means that I get a green followed by yellow. Okay. 6/10 times 4/9. Or I can get 2 greens, and that's 6/10 times 5/9. Or I can get a yellow first and then a green on the second draw. And that would give me 4/10 times 6/9. You'd add all those up and you'd get your probability of 13 over 15. Or you can do it in this fashion. To find the complement of the event, and the complement of at least one green is that both are yellow, right? That's the complement. Okay, not at least one green means that they're both yellow, okay? And so either way you do it, you'll get 13 over 15, all right? Okay, and then this tree gives us the conditional probability that we get a green card given we chose a green card on the first draw, and that's 5/9, straight from our tree diagram, okay? And then is getting a card, a green card on the second draw, is that independent of getting a green on the first draw? No, because we're doing this without replacement. So once we take that green card out of the deck, the probabilities change for green or yellow, right? Okay, and so we would get G2 and G1. Probability is 5/9. And then in the last one, I think I got confused here. I think I'm done with 5D. Okay, 5E. Are the two events independent? And you can see that they're not, okay? The probability of G2 given G1 is that the probability of G2, okay? And we know the probability of G2, that's just 6/10, all right? And the probability of G2 given G1 is 5/9, and that's not equal to 6/10 or 3/5, okay? All right. All right, so that's worksheet 3. It's a good overview